Have I already? Yeah, I got an email. I don't. I didn't say when I clicked on it. Is that why I got an email? Okay. Oh yeah. So, I have a confession to make. I photoshopped this one. This has been fabricated. And I just have to come clean, you know. It's not real. It didn't actually happen.
Exactly. No one needs a Taco Bell.
It looks pretty good though, doesn't it? I am quite good at the game, you know, fabricating.
It's okay. It's because everyone knows no one needs a Taco Bell.
I didn't actually eat there. I just tried. No, April Fools. This is real. I was actually at a Taco Bell. Actually, this was a couple of years ago in Texas, where my brother lives. He lives in Frisco, Texas. Is that next year? Texas. And we didn't actually know. We did not actually go to Taco. We wouldn't go there, but we were driving by. Apparently, there are people who keep it in business stuff, and I was amazed that even in Frisco, Texas, that there was a Taco Bell with this marquee on their billboard, on their sign. I was like, that's incredible. That's a unit that we do. And I took it a couple years ago, but of course I've cherished it, this photo ever since. And it's been in this PowerPoint. So that is in fact the true story. Yeah. Okay. So yeah, are you excited to start talking about sequencing in series?
Yes.
There was much rejoicing. Yeah. So we have sequencing series, and then our last unit is going to be polar and complex. And you might be thinking, then what? Do we have anything else to do in this year? It seems like that's kind of a quick end of the year. Well, these units, first of all, these units are a little longer than the other ones. So, I mean, I should say that longer than the last unit. That unit was kind of on the shorter side, right? Only 5 homework, so not as much content. I know there are only 6 homeworks listed, but they're going to take a while. And we have challenge problems too this unit. Get excited about the return of challenge problems. And there was more. What else do I want to talk about? Yeah, and then at the end of the year, I mean, more details will follow, but we're going to do kind of a review project at the end, and we also want you to take an entire IB exam, just for the feel of it. Obviously, there's certain problems you'll have to skip, but I want to hand you one so you can see what one looks like. Obviously, you have a little bit of a feel for that already. No. So anyway, we have some more things coming. I want to just make sure to set you at ease, because you might be like, I don't want to be bored after the last unit. Don't worry. Don't worry. We will take excellent care of you. Okay. So yeah, make sure you get the dates of those assessments down off that paper and into your calendar, subject, of course, to change as usual. Okay, so today we want to start talking about sequences a little bit. Starting in 9.4 is actually where this is in your book. So homework 1 tonight is what you'll do. And after today, I'd like you to do, well, I mean, some of this, I'm going to try and make this as rich as possible of an experience for you and try and do things that are interesting and new. But to be frank, today is the day where we review, like, most of the things, like, all of the things that I teach in my LP2 class in, like, 3 weeks today in one period, okay? So arithmetic sequences, we're going to remind you what those are, and geometric sequences. We're going to talk about the explicit and recursive definition, and then we'll also do something you probably wouldn't do in Algebra 2, and that's find the limit of infinite sequences as well. So all that in one 45-minute period coming at you starting now. Are you ready? Okay. So a sequence is an ordered progression of numbers. It could be finite, a finite sequence we talk about, or an infinite sequence. Or we could be more formal. It's just a function. Let's just remind ourselves that it's a function that takes as its domain usually the natural numbers or something like that, right? So sequences look like this, right? You know what sequences look like. One of these is finite. Which one is it? Is it obvious as the first one because there aren't like triple dots? We use this like triple dot notation, right? And the triple dots mean something. We should also say, we're using these kinds of notations, right? We talk about the first term of a sequence as being A1, right? Or U1, or whatever the name of the terms are. A2, etc., right? We usually index them from 1. That's not always true, but I think it makes sense. Generally, as a rule of thumb, people call the first term A1 and the second term A2, right, rather than something else. You wouldn't have to do that, but so I want you to make sure you understand that these are in fact functions. Instead of f of x, we write a sub n, though, right? But really, you could write a of n if you wanted. It would mean the same thing. N is the independent variable, and a sub n, the whole thing, a sub n is the dependent variable. Okay. So we have some different ways of writing. This is set builder notation, right? This is the set of all. We assume we should probably maybe also say k is a natural number or something like that, just to be clear. But this is a set of all k plus 1 over k such that k is greater than or equal to 1. So that forms a sequence, right? You plug in 1, plug in 2, etc. And you get a sequence of things. Wonderful. Not a lot of news on this slide. All right. We can define a sequence in 2 ways. We can use the explicit definition. Here's an example of an explicitly defined sequence. And an explicit definition is powerful. If we have one, it's nice. We don't always have, for many very important and awesome sequences that we might want to think about in life, no such explicit definition exists, though. But if we can get one, we prefer it to the thing that we're going to talk about in a second. And the reason is that if we want to find the 50th term, a sub 50, right, a50, then with this rule, it's easy. You just plug in 50 squared plus 2. The recursive definition is maybe what you most often find in nature and things like that. And if we can get an explicit definition from it, that's great. But recursive definitions are powerful and interesting as well. And they consist of 2 things: initial conditions and then a recursive rule of some kind. So this is the recursive rule down here for some sequence, right? And this is the kind of thing you'll see in a recursive rule. This guy here, u sub n minus 1, which you might read out loud in English as the previous term, right? If you wanted to say it out loud. So that means that, for instance, u5, if n is 5, u5 is equal to u4 plus 5. So what is the sequence doing? It's complicated notation, but what are we just doing each time to the previous term? Yeah, we're just adding 5, right? And of course, it's not good enough to just hand someone that rule. Hey, I've got this sequence where you add 5, right? That's not good enough. Can they recreate it just with that rule? No, they also need this initial condition, right? Or a set of initial conditions, possibly. We need more than one. So, what is this sequence? 3, and then 8, and then 13, right? We're just adding 5 each time. So maybe a complicated way to write that, but that's in fact what we're doing. Great. So this is the initial condition for n equals 1. Use this rule. For n greater than 1, use this rule down here. And of course, the complicated thing is if we want to know the 50th term of this, in this situation, we have a recursive rule. U50 is equal to U49 plus 5. Well, what's U49? Oh, U49 is U48 plus 5. Okay, we can bootstrap our way back down to U1 and eventually figure out what U50 is. That's like not a great strategy. But one could do it, and that would be what a recursive rule truly would demand if you were trying to use it to find the 50th term. Yeah, exactly. If we were dealing with this simple of a sequence, then we can write an explicit rule, and maybe we prefer that. Absolutely. Yeah, and we'll talk about that in a second. But recursive definitions can get complicated. Like we could have un is equal to u sub n minus 1 squared plus 2 times n squared. How about, I don't know, just for fun, right? That could be a rule. Do you think you could use this rule to come up with the 50th term of a sequence? Sure. I may also need to tell you U1. It's 21.8, okay? But once I do that, I'm just making stuff up. You could do it, couldn't you? What's U2? Well, it's just this number squared plus 2 times 2 squared, because we're on the second, right? You could use this. If you're trying to find the 50th term of this, it'll be the 49th term, once you've found it, squared, plus 2 times 50 squared, right? Does that make sense? So these can get more complicated is the point. And this one, maybe good luck finding an explicit version of this rule. How would we find the 50th term of this? I think you'd actually have to do it, right? I made it complicated enough that the explicit rule maybe eludes us. But if you're interested in studying that, you can do it. It's a whole. You can take whole courses in difference equations. That's what they're called. Sometimes you need a second initial condition. You guys know what's the famous sequence that requires 2 initial conditions? Fibonacci? Yeah, the Fibonacci sequence. So we need to initialize it, and then the rule is un is equal to un minus 1 plus un minus 2, right? Every term is equal to the previous term plus the previous term, right? Isn't that the rule for Fibonacci? You guys all know Fibonacci. So, and it usually initializes with what 2 for Fibonacci? 1 and 1, though there are other things you can initialize it with and get the same sequence, right? So you can figure that out. So anyway. Just a little word of things I think you already know. All right, so someone remind me please what an arithmetic sequence is before I put it up here. Someone say again what that is. Because I do know for sure, for a fact, that you guys have all encountered an arithmetic sequence in your life before. Right? Okay, Jerry.
So just like you add something.
Correct. Yeah, you add something each time. One term, you add something. You get to the next term. Exactly. That something is called D, is what we'll call it. And we call it the common difference because it's the thing you get. If you really do have an arithmetic sequence in front of you, it's the thing you get when you take any term and subtract the previous term, right? So it's and if it's really always the same number, let's call it the common difference. The recursive rule then is pretty easy, right? It's just one term is equal to the previous term plus D, right? And again, of course, you always have to say what A1 is, but right, so you'll have to initialize it as well somehow. And then the explicit rule, well, let's actually see if we can reason it through again, right? So we have some sequence 3, 8, 13, this is the one we were using earlier, 18, etc. Okay? So that's arithmetic, right, with the common difference 5. How would we write the explicit rule for this? We'd love to come up with an explicit rule for that. So this is maybe how I would think it through. How did you get to the second term? What did you do? You took the first term and added 5. How did you get to the second term? From the first term. You added 5 and then you added 5 again. So to get to the second term, you added 5. To get to the third term, you added 5 twice. To get to the fourth term, you added 5 3 times. So to get to the nth term, how many 5s do we need to add? N minus 1 of them, right? So that gives you this formula, and you just proved it in your head, right? It should make sense based on what we just said. It's not something you have to, I mean, you will memorize it, I'm sure, but it should just kind of make good sense why this works the way it does. Beautiful. Okay, with that in mind, let's try some examples. I'll try and make them interesting, but you know, like I said, this is stuff that you've done before, I think. I should remind you that, remember that an is the dependent variable, n is an independent variable, those are variables. And a1 and d, those are constants. Okay, so remember that all letters are not equal in that, okay? It's like y equals mx plus b. You understand m and b are constants, not variables. And x and y are variables. So with that in mind, let's try an example. I'm going to ask you a bunch of things about these two. And I'm going to promise to you right off the start here that these are both arithmetic. And I'm going to ask some volunteers to, not some volunteers, I'm going to pick some volunteers. I'm going to encourage some volunteers to answer the following questions. Give me the common difference for this, the 10th term, the recursive rule, and also the explicit rule for each of these. So starting with, let's start at least with the Common difference of the first one up here. Magali, you want to give us that? Where are you now? Yeah. 6. Okay. And then let's skip the 10th term for now. We'll come back to that in a second. Give me the recursive rule. How about Lisa? Over here. Can you give it to me? What would it be? Not sure. I'll give you the recursive one, the explicit one in a second here. Ryan, why don't you take the Ryan, you. How about you, Ryan, you? I got 2 Ryans right next to each other. That's my bad. Go ahead, Ryan. Give me the recursive rule.
So let's go with u subscript 1 equals -7.
All right, guys, I already committed to A, so okay. U1 is 7. Negative 7.
And then therefore an equals n minus 1 plus 6.
Right, and good. I'm glad you avoided the pitfall of not listing the first term, but you have to list the first term, right? In the box that I drew on the board, I want to be able to deliver that box to someone and have them be able to recreate the sequence, and you can't do that without the first term. Did you get the explicit rule, please? What do you think? We need a rule for an. Given the formula I gave you on the previous slide, just plug stuff in. What was it? A1? Yeah. Yeah, there we go. And if you want to simplify that, you can, but you don't have to, right? There it is. Wonderful. If you do want to simplify it, what would it be? An equals 6n minus 13. Yeah, that'd be great. Perfect. David, go for it.
For the recursive, do you have to explicitly say n greater than 1?
I mean, no, I won't be picky about that. But I mean, it's pretty obvious that if you tried to use this to compute 1, that you couldn't, right? Because you'd need to know A0, which no one is telling you. Yeah, you could find that and initialize it with A0. That's true. Yep. Yeah, I mean, like I said, we kind of usually default to 1 as being the first term, but for good reason. But 1 could easily talk about like a negative 5th term. One could, right? Yeah.
But with the recursive rule, with the sequence,
Yeah, you could actually claim that. You could initialize it with A4 or something, right? You could say A4 is -7, and then absolutely, you could do whatever you want. Yeah, like I said, we usually take the natural numbers to be the domain of the sequence, but I think it's fair to take the whole integers, all at negative numbers too. Jessica, give us the A10 then. Did you compute this? Where are you, Jessica? You just plug 10 into this. What do we get? And then this one over here, let's see if we can figure out what D is. D will come back to D. To A10 will compute, explicit, or recursive here, explicit. All right, we want to do the same things with this guy. Oh, wait a second. This one's not arithmetic, though, is it? Oh, it is? It is? Oh, you still my soul. All right. What? Speak to me, somebody. Tell me, justify yourself. It is? I don't see no 3 up there. I'm going to just try it out here. Log 18, how about minus log 6? I take any, if this really is, Mr. Chase, if this really is arithmetic, then I should be able to take any 2 terms, subtract them, and get the common difference. And you claim that's log 3? Yeah, it is. Do you see it? Do not forget anything ever. Okay. See if you can justify why he's right. Okay. Yeah, cool. Oh, wow. I love this problem now, Mr. Chase. I didn't realize what you're doing. It is arithmetic. Okay. That being said, give the recursive rule. How about on that? What would it be? That's fine. I'll do whatever you say.
No.
I mean, you don't. You can put it in whatever order you want.
A n minus 1 plus log 3.
That'll do. And the explicit rule. Let's hear from. I don't know. Why are you talking? Chris. What would the explicit rule be?
A sub n minus 1 plus log 2 n.
Wait, well, hold up. Hold up. Explicit rule? So we're looking for, what's the explicit rule? It's the first term, right, plus d times n minus 1 to count, right? So what would that be here? Just fill in the blanks.
Log 2
Okay.
plus log 3 times n minus 1.
Beautiful. There we go. I think that'll do it for us. All right. And just for fun, we could rewrite this, right? Using the same kind of spirit up here. Again, don't forget anything ever, okay? I might write this as log 2 plus log of 3 to the n minus 1, right? Can't we? This is an n minus 1 times log 3, so it can come up into the power.
You log 2 times 3.
Yeah, and then you could write log of 2 times 3 to the n minus 1 if you like.
No, I think the 2 would be up there.
No, it'll be inside.
Okay.
This is fine though in the box, but if you want to do something fun, you could do that. So A10 then, someone just tell me, like, what do we're trying to plug 10 into one of these? Any one of these would be fine. So it would be log 2 plus 9, log 3. Or you could use this formula down here. You get log of 2 times 3 to the 10. So 3 to the 9, excuse me. Right, whichever. We'll all agree in the end, though, that our answer is log of whatever that is. I don't know. Someone tell me. You got it?
Question.
Right.
If we write it for D, if we just write it in like the form that you boxed, is that okay?
Yeah, absolutely. Yeah. So, what is 2 times 3 to the 9th? I don't know. What is it?
39,366.
All right, we'll just leave the 10th term in that form, because if we were to take the log base 10 of that, it would be not something real nice, right? But that's good. I mean, all the other terms are in that form, so that's good. All right. What about geometric sequence? Someone remind me of the definition of a geometric sequence. Can someone do that? What do we mean by geometric? Right. Yeah, we have a common ratio, and what we're doing then, if you like you want to describe it to an elementary schooler, you'd say, yeah, you're multiplying by something each time, right? And you said or dividing, and just to be clear, we should have said that when we were doing arithmetic too. An arithmetic sequence is one where we add a number. But could it go downhill too? Yeah, if we add a negative number. So it don't need to be like, oh, an arithmetic sequence is where we add something. Or, oh wait, hold up, or subtract. Well, we don't have to like make that footnote, do we? Same here, right? We can just say multiplying by some common number r, and if we really mean dividing by 2, we'll say the common ratio is 1/2, right? So, yeah. So we can handle that situation here in a similar manner. Did I see a hand? Yeah. Maybe.
Just a question. Does the explicit function exist for any specific size?
That has a what? No. Yeah, like the one I gave you earlier. I don't think that you could find a closed form for the one I gave you earlier, though. U sub n equals, what did I make up? U sub n minus 1 squared plus 2n squared or something like that. I just made that up, and I don't think I could come up with an explicit rule for that. It might be for that one, but it would be very, very easy to come up with one by tweaking that even a little more to come up with one that you could come up with an explicit rule for. Very easy to do. Yeah. Huh? Well, because it's hard. No, it's often not possible at all. Yeah, no, some things actually have, it's proven, that some things are just plain hard, but that's a great, immature mathematical question to ask. Some things are actually, though, proven that a closed form can't exist for the explicit form of a sequence. So, yeah, so sometimes it's hard, like the Fibonacci sequence has an explicit form, but it's difficult. It's difficult to derive. It's not bad, but you could, but it is difficult to come up with. But it's not impossible in that case. But a lot of them are just straight up impossible. The recursive rule is, of course, pretty obvious. It's r times the previous term, right? The explicit rule, though, again, let's kind of like reason through. Like, say we have some sequence that is 3, and then we multiply by 5 each time. That's kind of similar to what we did before. 3 times 5 would be 15, times 5 again is 75, etc. Okay, so how do we get the second term here? We take the first term and multiply by 5. How do we get the third term? We take the first term and multiply by 5 twice, right? And how do we get the nth term? We multiply by 5 n minus 1. This sounds familiar, doesn't it? Yeah. We multiply the first term by n minus 1 r's. Right? So again, a formula that you'll have memorized, but it shouldn't be something that you're like, well, I'll have to memorize. Is it an n or is it n minus? Just think it through again, right? It should make sense why this is the way it is. The form of that equation looks very familiar to me. No, it's something that something that I just saw recently. Well, geometric is exponential, right? Like that's for sure. But I just saw it in a previous example we did somewhere. I don't know. Okay, I don't know. But you can go back and look and see if you see it anywhere. But all right, let's do the same thing again. Just kind of toy around with these concepts, make sure we're all solid on it. I'm gonna call on some people again. Second, same exact questions. Same exact questions. New sequences though. So I'm asking this time for the common ratio. Please tell me. For B, we'll come back to B. I'd like the 10th term. For C, I'd like the recursive rule. And for D, I'd like the explicit rule. And then we'll do the same thing for 2 as well. All right. So again, calling on some random people here. Josh, how about for the common ratio? Where are you, Josh? Thank you. All right, and then we're going to skip B, go down to C. What is the recursive rule? So you want to give it to me?
Sure. It's n equals 2n minus 1.
All right. Anything else you want to say?
Oh, and the first term is, I can see it. Okay, great.
Yeah, remember that's important even though it's done. Okay. All right. Good job. And how about Mona for the explicit rule?
A n equals A1 to
What's A1?
oh,
Times, oh sorry, what am I doing? Times 2 to the n minus 1. All right, yeah, that's great. And then someone plug in 10 for me to that. How about Irene, tell me what you get?
1,536.
All right. You could probably do that even in your head, maybe. All right. R equals something over here. So take a look, see if you can race ahead and answer these. What's that? Andrew, give me the R value if you can. It's trickier on here, right? It's -2. Okay. So can the R value be -2? We mentioned that yet, but in our discussion. But sure, it could be -2, and then we get this alternating sequence, right? Again, skipping B, jump down to C. How about Ryan C?
A1 equals A1 and then negative A1 equals -2 times
All right, wonderful. And explicit rule. Let's get Simon on that.
an equals -1/2 times
All right, beautiful. I will say one other thing though, just for fun, again, right? Just for fun, but full credit for that. But just for fun, we could play around with this a little bit too. I think it'd be fun. Isn't this equal to negative 2 to the negative first times negative 2 to the n minus 1? This guy here, negative 1/2, can be expressed this way, can't it? So that means this is another nice, really nice way to write this would be what? Negative 2 to the n minus 2. Isn't that a cool way to write that? Not required, but cool, right? Okay. And then where's Helen for the A10? Can you plug that in for me and tell me what you get?
Wait, what is 2 to the
Oh, that's why I'm asking you.
Wait,
512.
I don't think
What is it?
that would be
So
Or negative
negative 256. Wait.
256? Yeah, is it positive or negative? I know what you're thinking. Oh, it'll be to an odd power 9. But then we're going to multiply by
Oh, I
negative.
thought, okay, no.
So it'll be negative, but then it'll be negative, right? So I don't know which formula you're using, but I think it's a positive 256, right? Okay. It doesn't matter which of these formulas you use down here, whatever, you'll get plug 10 and you should get in all of them 256. All right. Anything else you want to say about that? I thought I heard something else. You good? Okay. All right. It's very convenient, isn't it? When you're given A1 and R, when it's like just obvious. But could you, given not that information, could you come up with it? This is a harder case that I might come up with. I give you just randomly 2 terms in the middle of the sequence. And I give you the second here and the 5th term. You don't know A1. You don't know D. You don't know anything, right?
It's negative 4 for it.
So how did you get that, though? Let's like bring people along with you, David.
I subtracted 7 from 3.
Okay, where'd you get the 7?
21 divided by 3.
And where'd you get the 21?
21 minus 3.
All right, absolutely. So I'm gonna do what he just did, right? So if it's arithmetic, right? We have 24 is equal to, just to be clear, A1 plus 4D, right? This is A2 and this is A5. And by definition, A5, the 20 is 24, because I told you so. And that means that if you plug in 5, right, isn't that what you get when you take the first term and add 4 of the D values to it? Don't you get the 5th term, whatever that is, 24? Likewise, if you, A2 by definition is, it's 3 here, right, is A1 plus just 1 copy of D. Isn't that what A2 is? And then this is what David is doing, right? You're really, and it's so simple to do on an arithmetic one that really, like David, you can probably do it in your head. I think if you were to forget this for a second, if you were just to do it using intuition, you'd be like, yeah, we got to cover a territory of 21 in the space of 3 terms, the common difference, right? You might think it through this way. But this is technically what you're doing. In your head, you're actually solving the system of equations. So if we subtract, I think that's the most natural way to solve this. We get 21 over on the left side equals, oh, isn't that great? A1's go away, 3D on the right side. And then we divide by 3, we get 7. And that's our common difference, like I said, which maybe intuitively you would have come to that realization too. But if you're doing it in your head, then actually this is, in fact, what you're doing, though. And then A1, you can go back to either equation, but we're mathematicians, so let's be lazy and use the easier equation, this one here. So A1 is negative 4. Okay, we're finally caught up to your amazing cerebral powers, David. Okay. Took a while, but we're here. Okay. All right. So therefore, the recursive rule is A1 equals negative 4, and AN equals AN minus 1 plus D, which is 7. And the explicit rule is, we just write these, I don't need to test you on it now. AN equals first term plus 7 times n minus 1, and feel free to simplify that if you like, knock yourself out. Okay, moving smartly along. How about B? What if we suppose that this sequence was actually geometric? You know, kind of to assume one form or the other. Well, I'm going to kind of take the same approach, right? It should be true that 24 is equal to what happens when we do A1 times R to the 4th, and 3 is what happens when we do A1 times R to the 1st, right? Isn't that like by definition? And then, in fact, right now we have, oh my goodness, we have a system of equations again. It's a nonlinear system of equations. Now we're big time. Well, it's not hard to solve, though. What might we do? Just subtract them, right? Or wait, that's not going to help here. Maybe divide them, though, because our goal is to maybe get rid of A1 or do something helpful like that. You could solve these systems, by the way, other ways, right? You could solve it by substitution or something, too, but I think this is the easiest way. And again, if you were to like forget this method, if you were to just like approach this and say, I'm just going to use my intuition, you probably would be like, multiplicatively speaking, I have to cover ground of size 8, right? You might have that intuition. And over on the right side, we have our cubed when we do the division, right? A1s cancel out when we divide, and we have our the fourth over our the first. So we have to cover a ground of, like, multiplicatively speaking, of 8, of size 8, and we have 3 terms to do it. So that's our intuition. What's R? David, can you sit down, please? Just pretend like you're paying attention. Thanks. All right. And then what's A1? Go back and solve one of the equations. How about the simple one? We now know that R is not R, it's 2. So A1 is 3 halves, and we can write our rules, right? Why don't we breathe there just for a second to make sure everyone's okay? Everyone all right? Totally. I'm about to write the recursive explicit rules. You guys can do it if you want. But we just did a lot, and like I said, this takes me like a week to teach in a low-level class. But you guys will hopefully remember this kind of stuff a little bit. But we are covering a lot of stuff today, so I want to respect that. You could write this other ways too, but that's good. Okay. Anything else you want to say about that before the next class, the thing I want to say something about is infinite sequence. We're going to change gears just a little bit. Yeah. Yeah, in fact, I'm recording again too, so everything you could possibly want will be on the internet. Fonda, there you go. Actually, the PowerPoint's already on that line. I think I put it up earlier. I know, sorry, I'm going a little quick right now. All right, so let's talk about limits of infinite sequences now. We've got that ... at the end, right? So, and before we even say anything about these, we should say something else, right? We should say that there are lots of other sequences in life besides just arithmetic and geometric ones. It just so happens that we like talking about arithmetic and geometric sequences so much because we can say so much about them, right? We have explicit rules. They always behave in a very certain way. Tomorrow we'll give you formulas to sum them up, right? Like, there's lots of nice things we can talk about, but not every sequence in life that we encounter is arithmetic or geometric. So some of the ones I'm going to look at in a minute are not necessarily arithmetic or geometric at all. So for a sequence ... that goes to infinity, we might be interested to know or to discuss what would happen if those terms get closer and closer to some number, call it L, right? If they always get progressively closer to a certain number, then we might say the sequence has a limit. That would be our L value. And if that's the case, then we might use this notation to say it, right here, right? Which is a notation that I think you're already familiar with, right? From first semester. I know we've talked a little bit about that notation. The limit as n goes to infinity of an is equal to L. And if that's the case, we can write that, and we also say that the sequence that we're dealing with converges. Or you could say converges to L, right? And in the case that that's not true, we say that the sequence diverges, right? So just to be clear, the other case, I mean, I don't even necessarily have to write what this is. If that's not true, it diverges. It either converges or it diverges. It doesn't. You don't have one that does both. Right? Two camps. The limit could diverge in a couple different ways, though. So it could go off to infinity or negative infinity, or it could just bounce around, right? So, and this might sound like a really high and lofty idea, but in fact, it is just finding the horizontal asymptote from first semester on the right side of a function, right? All the things you know about horizontal asymptotes come right back into play right now, okay? So if you can come up with an explicit rule, then you can use that just like we did a function first semester. So I'd like to have you bring back to mind now, because I need them. I need you to bring back to mind how to find horizontal asymptotes for things like exponential functions, rational functions, right? Remember all the rules that come into play when things go to a certain number. So that's the big key here, right? Is this, I know it sounds kind of, whoa, infinite sequences, but really you've done it before in a different context. Star that. Anyone want to say anything? Andrew wants to say something.
Could you explain why some of
It's not true in a formal sense, but we can discuss it later. We haven't discussed series yet at all yet, right? We're only dealing with sequences. Not yet at all have I asked you to add anything up at all. So we'll table that question. I do have comments about it for sure, but I'll save them for maybe not even tomorrow, but when we come back from break. We won't deal with infinite series until after break. It's going to be a big topic of this unit. Yeah.
Why are the horizontal asymptotes on the right, not the left?
Well, because again, we're thinking of the limit as n goes to positive infinity, right? That corresponds, that's the definition of the horizontal asymptote on the right, right? But you could also ask, you could ask what happens when n goes to negative infinity, but this goes back to the discussion. We usually, in a sequence, think of regression out to infinity, positive infinity, just because of the way we conceptualize sequences and why we use them in life. So let's ask this question, does this converge or diverge with the following examples, just for fun, okay? So the first one I even gave you the explicit rule for. I don't think you would need it though. It's 1 over 1, 1 over 2, 1 over 3. Is it obvious that it's 1 over n? And if that's the case, then what I'm inviting you to think about, based on my last comment on the last slide, is I'm inviting you to think about the following limit that you evaluated first semester, right? I know it's like in the new context of sequences, but really this is a pretty simple question. What's the answer? Yeah, you can even, in your mind, you can't even resist thinking about the graph and everything, right? It's all there. It's all there, isn't it? Because you're good math students, okay? L is 0, right? This converges, and we can say it converges, in fact, to 0. Wonderful. This one I didn't give you the rule for, but maybe you can come up with. It's not too bad, considering the one we just did. The denominator is still n, but the numerator is n plus 1. Is that clear? So there we go. Sometimes I might not give it to you, and you might have to come up with it. And by the way, let's just pause and appreciate what we just did. We just came up with an explicit rule for something that's not arithmetic or geometric. Whoa! Now we're talking. All right, it wasn't that hard though. Okay, but one can still do it sometimes, right? For sure. What's the limit? Is it obvious to everyone that it's 1? Just intuitively, maybe it feels like 1. I mean, it's already feeling like 1, isn't it? Like by the time we get out to a million 1 over a million, you'll be like, yeah, this is basically 1, right? So yeah, this converges, and it goes to 1. We can use something other than just intuition, though. Remember all of our rules from first semester, right? With rational functions, and degree on top and bottom, and all that stuff. Yes? What's the rule here? It's arithmetic. What is it? Okay. What's the rule? Can we say it? What's the boil it down? What is it going to be? Some of you are thinking really hard here. So what does that come out to be? Don't use the formula if you can just look at it too. You're right. The formula works. Okay, 2 plus 2 times n minus 1. It's just 2n. Okay. Maybe I shouldn't have been so mean. Okay, but that's what you'll get. That's your formula works too. Okay. Any arithmetic sequence is like, right? Arithmetic sequences are just linear functions, aren't they? Geometric sequences are just exponential functions, like Tom said earlier. Yes. So anyway, so this is linear. You got a line we're thinking about here, 2x, if you want to think about it, right? What is the limit as x goes to infinity? Is it even worth talking about? It's infinity, or we might just say it diverges, right? But again, we're resting very heavily on your prior knowledge of functions in general, right? How about this guy, d? Yeah, what would we say here? The series doesn't converge either, actually. So this diverges, right? Because it doesn't go to a single number, right? Can you name the number it goes to? Okay, then it diverges, right? And what's the last one? Is it 5 halves based on your, sorry, I shouldn't say equals, L, the limit equals 5 halves, right? Based on your